He has been leading research on end-to-end speech recognition, end-to-end text-to-speech, natural language understanding, natural language modeling, speech enhancement, keyword spotting, and so on at the Samsung Research. I mean, he's, I would say, he's probably the most prolific researcher in speech in Korea, because he did his PhD under a very famous professor at CMU, Richard Stern. His advisor was Richard Stern. So he did a PhD in speech. Before he did his PhD, he did his master's at Seoul National University under Professor Song Won-young, who was also a speech person. After graduating from CMU with a PhD, he went to Google to do speech at a speech research lab. Okay? And Samsung Research scouted him from Google. So, he's been doing speech all his life, and I don't think there is anyone who has done more work in speech recognition, speech, anything that's related to speech. So, it's a real pleasure to have such an expert and someone who has been so knowledgeable, who has been in both academia and also in a company, a corporate company. So it's a real great pleasure to have him here, and today he's going to give us his research topic or the area that he's most interested in. He'll probably provide us with some insight. Let's welcome Professor Kim Chanwoo with a warm applause. Just say, he will be presenting most of his stuff in Korean, but because we have a special guest, I mean, he's going to make some English. And his slides are in English. Thank you very much.
우선 초청해 주셔서 감사드리고
Thank you very much. So, my name is Chanwoo, as introduced, and this is my greatest honor to have a chance to talk here. So, actually, I prepared the slide very quickly, so I didn't have a lot of time to prepare for today. But Daniel, for me, it's one of my greatest honor to have a chance to talk here. So today I'll briefly talk about some latest advancements in speech recognition. So I'll discuss all neural speech recognition engines based on the CTC algorithm and also RNN transducer, and we will also discuss self-supervised learning techniques for speech recognition, and I will also discuss how the generative models can be incorporated into speech models as well. And in the past few years, we have focused on reducing the model size, especially for on-device speech recognition or on-device NLU. So I'll briefly talk about efficient optimization. 그래서 제가 영어로 좀 강의를 준비를 한 것은 아니어가지고 외국 분도 계셔서 한국말도 하고 그다음에 영어로도 하면서 강의를 진행하겠습니다. 네. So I first start with a short introduction, and after that I'll discuss some well-known speech models. So as you probably know, for end-to-end sequence processing, one of the most widely used structure might be the encoder-decoder structure. So in speech recognition, we can also use the encoder-decoder structure. Or we can also use the encoder-only structure as well. But if we use the encoder-only structure, then the limitation is that the output ranks of the model will be determined by the input ranks. So decoder has the power of controlling the output sequence ranks, but the encoder doesn't have such kind of capability. So in encoder-only structure, we need to use a specialized loss function like CTC. So in today's talk, I will briefly talk about CTC loss. But in CTC, we don't have any feedback path, so it's not an autoregressive structure. So to tackle that problem, Alex Graves proposed an approach called RNN transducer. So these days for commercialized speech recognizers for Samsung or Google, we have been using speech recognizers based on the transducer structure. So more specifically, we have been using conformal transducer. So in today's talk, I will also describe the structure of the conformal transducer as well. And as you probably know, these days large range model is especially popular, and we can extend the modality of the large range model by adding some speech tokens as well. So as an example, we can create some speech tokens using encoder-based approaches like Hubert. Then we can create some discrete speech tokens. Then we will have both the language token and the speech token. Then using both speech and language tokens, that we can build a kind of generative speech and language models. So I will talk about these topics in section 4. And in the final section, we will briefly discuss the model compression techniques. So previously for model compression, famous technique might be LRA. So LRA stands for low rank approximation. But these days, I think the more popular approach might be quantization. So when I was working for Samsung, we did 8-bit quantization. But these days, people have been using 4-bit quantization. So if you are familiar with large range model, that you probably heard about some papers called GPTQ. So in GPTQ paper, they achieved 3 or 4-bit quantization, and these days people are trying 1.58-bit quantization. So we can significantly reduce the model size, and we can also reduce the computational cost. And also there are some pruning techniques as well, like layer pruning or head pruning to reduce the model size. So I will also discuss those pruning techniques as well. So first one is introduction. So I prepared a slide of our demonstration. So we did commercialization, on-device speech recognition commercialization in 2019, and at that time we used the MoCA-based approach. MoCA stands for monotonic unchunkwise attention. So to enable streaming capability in the encoder-decoder model, we use the variation of the attention mechanism. So we adopted MoCA attention. So in today's talk, I will briefly talk about the MoCA attention. So MoCHA. And later on, we commercialized the RNN transducer speech recognizer in 2021. And in 2022, we commercialized both on-device and cloud speech recognition engines based on the conformal transducer. So conformal stands for convolution augmented transformer. So as you probably know, in transformer structure, we have the multi-head attention, and on top of the multi-head attention, we had the feed-forward module, so we have a lower dense layer and the upper dense layer, and we have the activation in between those two layers. But in conformal structure, we are additionally adding a convolutional module as well. So conformal itself means convolution augmented transformer. So these days at Samsung and Google, the speech recognizer structure is based on conformal. But as you probably know, these days, large language model is really popular. So the research focus at Google or Samsung, Google or and Microsoft is actually using large language model to add some speech token as well. So the research direction might be creating a kind of a multimodal generative speech language model. So in our lab, we are also doing some research into this direction as well. So in this slide, you can see some paradigm change in the past 10 years. So there are three different colors. So blue colors show some important algorithms related to language processing, and the orange color means some important algorithms in speech processing, and the green color means some important algorithms that related to multimodal processing. So in speech recognition, RNN transducer paper was published in 2013 by Alex Graves, and when I was working for Google in 2015, at that time some intern students like William Chan started working for using the attention-based encoder-decoder structure to do speech recognition. So encoder-decoder structure was proposed in 2014, and the attention-based encoder-decoder structure was published in 2015 for machine translation. And 1 year later, people started using attention-based encoder-decoder structure for speech recognition as well. And as you probably know, for speech synthesis, people started using WaveNet. So this work was also published by Google DeepMind paper. And Tacotron is the acoustic model part of the Neural TTS, and it was also published by Google people. So actually, the first author of the Tacotron paper is Yushan, and he used to be the intern student in our team. So I closely worked with him when he was an intern when I worked for Google. And Transformer was also published by Google researchers in 2017. So the paper appeared in archive in 2017. So as you probably know, between 2014 and 2018, actually Google made a huge contribution to the advancements of artificial intelligence. And the third paper appeared in 2018, and this one is a very important paper because previous BERT algorithm, people usually used supervised data set, but in case of BERT, people started using self-supervised data set. So they started using unlabeled data. So they used the next sentence prediction and also next language model to train the BERT structure. But later on, it turns out that next sentence prediction does not play an important role. So for encoder-based structure, masked language model might be one of the most important criteria. But next token prediction is important for decoder-only structures like GPT. And Google P5 is a self-supervised approach applied to encoder-decoder structure. So people started using the self-supervised training technology to the encoder-only structure like BERT and Google T5, which is based on the encoder-decoder structure, and the decoder-only structure like GPT. And when GPT first appeared in 2018, I think that it was not that popular, but in 2020 when GPT-3 appeared, actually it was a huge hit. So that algorithm became a very popular. And in Korea, some companies like Naver and LG AI Research started working for large language model as well. And at Samsung, we started training large language model from 2022. So in our team, we started training large language model from 2022. So we started building the fully neural sequence based approach, speech recognition and the speech synthesis engine in 2018, and we commercialized those engines in 2019. And for large language model, we started from 2022, and it was commercialized early in this year. And as you probably know, these days, multimodal approach is also popular. In language, actually, self-supervised training might be more straightforward because the texts are based on token. So token is a kind of subword unit. But in case of speech, actually speech data might be a kind of continuous data, and there's no clear boundary between two phonemes. So usually the time boundary is not well defined, and also there is not well defined unit. So it was not that straightforward to apply the self-supervised training technology. So to apply the self-supervised training technology to speech, it took some years. So the first successful paper might be Wave 2.0. So their paper was published in 2020. So it also showed a significant performance improvement when we don't have a sufficient amount of labeled data. And after Wave 2.0 was published, there were some follow-on research like Hubert or Wave LM and so on. And at Samsung, we did commercialization like on-device speech recognition based on the vocal structure, RNA transducer, and as I discussed before, conformal transducer structure, and also PTS. So we used Tacotron based structure for acoustic model, and for vocoder, we used the structure based on LPCnet, and on-device Gaussian translation was commercialized roughly in 2021. And as you probably know, on-device LLM was commercialized for high-end Samsung phones. But at this point, actually, on-device LLM commercialization might be applied to some limited scope. So original target was applying LLM to various kinds of tests like text summarization, Gaussian translation, and so on. But we first commercialized on-device LLM only for style conversion, text style conversion. So originally our intention was applying LLM to spell correction, Gaussian translation, and so on. But for those kind of tests, actually, the performance of on-device LLM is not good enough. And for Gaussian translation, usually LLM-based approach is doing better than the encoder-decoder approach in terms of context understanding. So they are better at analyzing the context, but at the same time, hallucination problem still occurs. So that's one downside of the LLM-based Gaussian translation approach. So at Samsung, we commercialized Gaussian translation based on the encoder-decoder structure. So the structure is not based on LLM. So let me first start with some basic speech recognition structure. So speech recognition is a kind of sequence-to-sequence technology. So the input is either waveform or acoustic feature sequence, and the output of the model is the text. So text consists of a sequence of tokens, and a token is defined to be a subword unit. So usually we use the algorithm like BP or unigram tokenization approach to define the token. And for speech recognition, those are widely used structures. So encoder only structure, and in the middle figure you can see a structure based on the transducer, and here you can see the structure based on the attention-based encoder decoder. And you are probably familiar with the encoder only structure and also attention-based encoder decoder structure, because those structures are widely used in language processing. But I think that transducer structure is only used for speech recognition. So I will mainly talk about transducer-based structure in this page. So in transducer-based structure, we have the encoder which in green color, and we have the prediction network. So the purpose of the prediction network is predicting the next token. So the role is quite similar to the language model. So the role of the language model is actually predicting the next token. So the role of this part is quite similar to language model. So the idea of the transducer is we have a very small language model and we have the speech encoder, and those two networks are combined using the joint network, and we have the softmax on top of the joint network. So the structure is quite simple. So the idea is just like combining speech encoder with a small language model. So in the encoder-based structure, this one is the conformer-based encoder. Then usually we have a convolutional downsampling layer at the bottom. So the bottom layer is the spec augment, which is a kind of data augmentation or regularization technique. And on top of spec augment, we are doing convolutional subsampling. So we apply 1D CNN filter to reduce the feature length, and after that we apply the conformal block. So usually we are applying two layers of convolutional subsampling layers, and in each of convolutional layer, the stride size is 2. So the net effect is downsampling by a factor of 4. So so you can see that in the encoder-based structure, it doesn't have the power of controlling the output sequence length. So the output sequence length is determined by the different lengths, but because we have the convolutional subsampling layer, so there is no guarantee that the output length is the same as the different lengths. So in this diagram, I represent the output length by T sub out, and the different length is T sub in, and I is the example index. And in the encoder-based structure, one difficult part is that the model output sequence length might be different from the ground truth sequence length. So ground truth sequence length is defined in terms of the tokens. So this one is based on the text, but the model output sequence length is based on the acoustic sequence length. So there is a mismatch between the ground truth sequence length and the model output sequence length. So we should come up with a kind of alignment algorithm between the ground truth sequence and the model output sequence. So for speech recognition, we have a very long history to tackle these problems. In old days, like in 1960s or 1970s, people started using pattern matching approach, like dynamic time warping or dynamic, which is based on the dynamic program approach. And after that time, people started using hidden Markov model approach. And in the neural network era, people started using encoder-decoder structure or CTC laws. So in today's talk, I'll describe the CTC and the RNN transducer laws a little bit. So in this page, convolutional subsampling is described, but because I already talked about convolutional subsampling, I'll skip this page. So in conformal block, the structure is quite similar to the ordinary transformer block. So if you see the transformer block, then usually at the bottom we have the multi-head attention module, and on top of multi-head attention module we have two dense layers. So one layer is actually usually expanding the dimension by a factor of 4, and after that we apply some activation, and the dimension is reduced back to the original dimension by reducing the dimension by a factor of 4. But in conformal structure, we have two feed-forward modules, and we have additional convolutional module. So in conformal structure, that's the difference, and the reason why we added the convolutional module is because if we use the CNN structure, then CNN has a better capability in capturing kind of short-term context, and the transformer network might be better in capturing long-term context. So in speech recognition, short-term context is also equally or even more important than long-term context. So we are using both some convolutional module and the multi-head attention module. And in transformer structure, we usually use the positional encoding, but to commercialize speech recognition, actually the attention should be a streaming attention, and in that case, instead of using absolute positional encoding, we are usually using relative position encoding, because we are usually dealing with limited context attention. So for that purpose, we are usually applying positional encoding, relative positional encoding, but when you commercialize the conformal structure, we switch the location of the conformal block with the multi-head attention block. So if we place the conformal block below the multi-head attention block, then CNN actually understands the sequence information, even though multi-head attention doesn't have the capability to capture the sequence information. So we needed to intentionally add some positional information. So if we switch the location of the conformal block convolutional module with multi-head attention module, then the advantage is that you don't need to add relative positional encoding information. So when we actually commercialized our conformal structure, we placed the convolutional module below the multi-head attention module. So because lack of time, I'll skip this slide. So in the conformal, we have 4 modules, and each module is represented using this kind of components. So the structure itself is quite similar to the original transformer structure. So as you can see, in the feed-forward module, we have 2 dense layers, and we have 1 activation. So in the original transformer paper, we have the value activation, and in conformal we are using the switch activation, but those kind of things might be a kind of a minor change. So there's only small performance difference coming from the switch from the value activation to switch activation. And convolutional module is introduced in conformal structure as I discussed before. So MHSA module and feedforward module already exist in the transformer structure, and in the conformal structure we are also adding the convolutional module to better understand the short-term context. So let's skip this slide. So this is a review of the skeleton potential. So I think that you might be quite familiar with the transformer structure, so I'll skip this. So if we use the conformal structure, we have the length mismatch issue, as I discussed before. So let me explain how we can handle this issue. So Alex Graves published a paper titled Connectionist Temporal Classification, and in this algorithm he actually considers all possible alignments between the model output and the ground truth sequence. So he's considering all possible alignments. So if we just compare the waveform and the text sequence, then it's not quite straightforward to find out the location corresponding to a certain character. So we don't have information about where the text Y is located in this waveform. So in CTC, you are considering all possible alignments, and you are calculating probability along these all possible alignments, and those probabilities are added up. And in statistical algorithm, the author also included the blank label as well. So blank label is inserted to handle some non-speech portion like silence or some background noise. So in this page, you can see an example of the alignment. So here, x-axis is the time, and the y-axis represents the sequence index in the text sequence. So this one represents the label sequence index, and the x-axis represents the time index. So the alignment is like a path starting from bottom right position up to so bottom left position to top right position, and it consists of segments. So we can consider alignment function Q. So alignment function is considered as a kind of random variable. So the alignment function itself can be represented as a sequence. So once we have the alignment function, then the role of the alignment function is mapping the temporal index to the token index. So that's the role of the alignment function. Then the time aligned ground truth sequence will be obtained in this way. And then we can also consider the time aligned ground truth as well. So we don't have the knowledge about what might be the ground truth at a certain time point, but you can calculate the probability in statistical algorithm. So by using the alignment function, then from the ground truth label, we can convert the ground truth label sequence into time-aligned ground truth label sequence. So in CTC, we are considering all possible alignments. Then we can convert the ground truth label sequence into time-aligned ground truth label sequence. So if you compare those two sequences, then the biggest difference is that in this sequence, the sequence index is L, which is the sequence token index, but in this sequence, the index is time t. So by using the alignment function, that we can convert the label sequence index into time-aligned ground truth label sequence index. And the alignment constraint is that we can skip the blank symbols, but we cannot skip the real token. So as long as this constraint is satisfied, we can consider any alignment starting from the bottom left position to the top right position. So in CTC, there may be many possible alignments. So those are some examples. So in CTC, the probability is calculated by adding up all those probabilities. And fourth probability is the partial probability starting from the bottom left position to a certain point in this two-dimensional plane. So the time index is t, and the label index is L, and the fourth probability is calculating the partial sequence probability, and the backward probability is doing the opposite stuff. So once we define the forward and backward probability, if we multiply the forward and backward probability, then it means that we are multiplying those partial sequence probabilities. So the meaning is that we are considering all possible alignments starting from the bottom left position to top right position, but the constraint is that the path should go through t, L. So t is the time index, and and L is the label index. So if we multiply the forward and the backward variable, then it means that we are basically considering all possible alignments, but we have one more constraint. That constraint is that the path should go through t, L. So t, L is one point in this two-dimensional plane. And the reason why we are using forward and backward variable is because we can calculate the forward and backward variable very efficiently by using the conditional independence assumption. So we can use a recursion equation to calculate the forward and backward variables. And if we add up the multiplication of the forward and backward variables from the label index 0 up to the final label index, then that value is the same as the entire CT probability itself. The reason is when you consider those paths, then as certain time t, then the path should go through this point or this point or this point up to this point. So if we consider all possible points from bottom to top, then it means that it will be the entire probability itself. So if we add up the product of the forward and backward variable, and if the summation is done from the lowest label sequence index to the final label sequence index, then this value is the same as the entire citizen probability itself. And in machine learning, basic machine learning course, I think that you are probably already familiar with this kind of equation. So when you have the cross entropy loss, and if we use the cross entropy loss, and when we are using the softmax layer, then if we differentiate the cross entropy loss with respect to large, so large vector is the input to the softmax layer, then the this gradient value is true value subtracted by the estimated value. So if we do actual differentiation, then you can derive this equation easily. Then from this equation, then we can see that in the previous definition of the fold and backward variable, I mentioned that if we multiply the fold and backward variable, then it means that it's all possible alignments, but the constraint is that at time t, it should go through t comma l, and the denominator is the entire probability. So the meaning of this numerator is that it considers a subset of the alignment, and the constraint is that at time t, the label index should be j. So the estimated label at time t is obtained in this way. So in CTC loss, the calculation is done in this way. So the derivation shown in this slide is a little bit different from what Alex Graves derived the differentiation of the CTC loss with respect to the large vector, but the final result itself is the same. So I already talked about the conformal structure, so I'll skip these two slides. So previously, we usually start from full scratch training using the labeled data, but after the introduction of BERT, the research direction has been changed. So self-supervised training is very popular. So we first start with pre-training using large amount of unlabeled data, and after we obtain the pre-trained model, then we are usually applying fine-tuning using relatively small scale labeled data. And in speech, one popular structure is Wave-2-Back 2.0. So in Wave-2-Back 2.0, the structure is quite similar to BERT, but in text, we can define the text unit. So usually characters might be the smallest unit, and in text, grapheme is actually the smallest unit, and grapheme is very similar to character. So basically, character plus some punctuation marks can be considered as a grapheme, and the group of grapheme can be considered as a kind of token. So in text processing, we have well-defined units, but in speech, the difficulty is that the input data itself is continuous, so it's not tokenized, and also we don't have a clear boundary between two phonemes. So in Wave-2-Back 2.0, the authors introduced vector quantization technique to define the token, and masking is done, and the contrastive loss is used, and that approach is somewhat similar to BERT. So I think that you might be familiar with the bidirectional encoder representation from transformer. So in BERT approach, they use the mask range model to predict the masked portion. So by using Wave-2-Back 2.0 approach, just using a small amount of labeled data, we could construct a high-performance speech recognition engine using the CTC laws. So in the pre-training stage, the author used the contrastive laws and the diversity laws, and the masking is done. So the objective is predicting the masked portion. So the idea is similar to BERT, and they use vector quantization. So as I mentioned before, in Wave on 2.0, they are using both contrastive laws and diversity laws. And if you see the diversity laws, then actually this one is very similar to entropy. So if we don't include diversity laws, then there is a danger of selecting only one code element from the code book. So our objective is equally selecting all possible code book elements. So we introduce diversity laws to have a more uniform code book selection. So and they also use the Gumbel softmax trick. So they are doing a vector quantization, and in the vector quantization, basically the operation is selecting one element which is most likely, but argmax operation itself is not differentiable. So they use the Gumbel softmax trick, which was already used in some famous approaches like GAN. So then by using the Gumbel softmax trick, then the operation can be differentiated. So they use the Gumbel softmax trick. So after the introduction of Wave 2 on 2.0, people started using Hubert. People developed Hubert and also Wave MM. So these days in our lab, we are doing speech recognition experiments using Wave 2.0 Hubert or Wave MM. So those are pre-trained models are useful not only for speech recognition but also for other tasks like speaker identification and verification. So as an example, previously for speaker identification or verification, people used some kinds of VAE-based approach like X vector or D vector, but these days people observe that feature information obtained from pre-trained LM is actually performing better than X vector or D vector. So those kind of pre-trained speech models are important not only for speech recognition but also for other tasks like personalized TTS or speaker identification or speaker verification and so on. And I said that you might be familiar with attention-based structure, so I'll skip this. But in attention-based structure, one difficult problem is that we cannot do streaming speech recognition because the decoder will start operating after all the input is encoded. So streaming speech recognition is not possible. So one approach to tackle this problem is the MoCA approach. So at the beginning of this talk, I talked about MoCA. So MoCA is the acronym of the non-occurring unqualified attention. In MoCA approach, there are two layers of attention, and in the bottom attention layer, we are finding the point where the current location should be defined. So in this page, then you can see the diagram. So the x-axis is the input time index, and the y-axis is the output layer index. So in the lower layer, it defines the attending point. So in speech, as the speech proceeds, the corresponding text label index will also increase. So the relation is kind of monotonic. So they are using this kind of monotonic characteristic, and by using the attention weight, so if the attention weight is larger than certain threshold, then we define the current location corresponding to the next token. So the monotonic attention works in this way. So in the earlier slide, I talked about the transducer structure as well. In transducer structure, the difference between the GTC-based structure, the biggest difference from the CTC-based structure is that the output has both the time index and the label index. So in the CTC-based structure, we only added the time index, but here the softmax output is two-dimensional. So we have the both time and label index, and we have the joint network, and I mentioned that this part corresponds to the prediction network, and the rule is similar to the language model, and we can see the encoder structure on the right-hand side, and in the joint network, these two networks are joined together. And when joining is done, the dimension actually increases. During the training time, the dimension of the prediction vector will be B by L by D. So L is the length of the label, and D is the model dimension, and B is the batch size. And on the encoder side, the dimension will be B by T by D, and B is the batch size, and T is the temporal sequence length, and D is the model dimension. And the vector of applying the joint network, the dimension will be B by T by L by D, or B by L by T by D. So the dimension will be increased to include both the label sequence and the temporal sequence. So dimension will increase, and we have both the temporal index and the label sequence index. So the softmax definition is similar, but this one is a two-dimensional softmax. So you know that softmax is defined to be the normalized exponential, and here it's still the normalized exponential. So in H value, we already applied the exponential operation, but here the difference is that we have both T and the label index. So softmax is a two-dimensional softmax, and in the transducer structure, the author also defined the null output case. So as certain time is possible that we don't generate any output. So in CTC-based approach, the author used the blank symbol, but in transducer-based approach, the author defined the null output case. So it's still on two-dimensional alignments, starting from the bottom left point to the top right position. But the difference is that in the GTC loss, the temporal time index will always increase, but in Rn and T, in transducer structure, it's possible that we are just going straight up, like this one, and when the position goes from here to here, then it corresponds to null output case. So to generate certain label at a certain time, then the direction should be always onward direction. So based on this assumption, the forward recursion can be represented in this way, and backward recursion can be represented in this way. So the differentiation of the loss is obtained in this way. So if we use the definition, so in Baran and T, if we multiply the fold and variable, then it's the same case as GTC case. So it considers all possible alignments starting from the bottom left point to the top right point, but it should go through T comma U, and in this case the summation should be done using this equation, because in this case we added up the probability going through this point, this point, this point, and this point. But in Rn and T, actually some paths can go through both here and here and here. So if we get the probabilities along this direction, then certain paths will go through all these points. So when we are getting up probabilities, then we should get a probability going through here, 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 in this diagonal direction. So in transducer, the probability is defined in this way, and I will skip the mathematical detail, but if we do differentiation, then we can come up with this equation. So the final differentiation will be obtained in this way. So in transducer structure, the gradient of the loss can be obtained similar to the GTC case, but the difference is that the dimension will increase. So when we actually implement the transducer loss, actually it requires much more memory compared to the GTC loss case. So our commercialized speech recognizer engine is based on the transducer loss, and in the actual commercialized engine, in the top layer, we use the bidirectional STM or full attention. So in the lower layers, we use the either unidirectional STM, or these days we are using limited context of attention to enable streaming speech recognition. But to improve the speech recognition performance, so on the top layer, we are using either bidirectional STM or we use the full attention. So now let me briefly talk about some language model stuff, because to discuss the generative speech model, that we should start from some language model, because language model itself will be extended to include the speech tokens. So I will briefly talk about the language model, but because I already talked about multi-structured best language model, I will skip this slide. So in BERT, we are using the best language model structure. So we are masking out certain portion of the input, and our objective is predicting those masked portion. So BERT is based on the encoder structure. So those are token embedding, segment embedding. So in the original BERT structure, actually two sentences are given as the input, and it also the next sentence prediction, NSP. But as mentioned before in later papers, right, Robert, it turned out that next sentence prediction is not that important for pre-training. So actually, best language model is the most important part of BERT training. But these days, decoder-only structure is popular. So generated pre-trained transformer is also based on decoder-only structure. So if you see the transformer structure, then it has both the encoder and decoder. And in GPT, they are only using the decoder part of the transformer. So here you can compare the structure of the bolt and the decoder Rooney model. So in bolt structure, the name itself means a bidirectional encoder representation from transformer. So it's a bidirectional attention, but in decoder omni structure, it's a kind of causal attention. So the attention mechanism only depends on the past. In current speech and language models, we have several components like speech recognition model, speech synthesis model, machine translation model based on the encoder-decoder structure, and the Q&A model, energy model, summarization model, topic classification model, spell correction model, and action planning, schedule extraction, and so on. So previously in Samsung actually those were implemented using each discrete component. So those are discrete components. So one component is completely separated from the other. So we need to have a lot of those components. But if we use a large language model, then our long-term goal is replacing the entire NLP task with a large language model. So a single model can handle all these kind of tasks. So in the large language model, as you probably know, supervised fine-tuning is done, and RLHF or RLAI can be done. So 여기서부터 그 슬라이드가 한국말로 지금 되어 있는데요. 스피치 GPT 경우는 LLM의 기반도 있는데 LLM에다가 스피치 토큰을 추가를 시킵니다. 그래서 스피치 토큰은 아까 그런 인코더에 기반한 그런 슈퍼바이즈드 어프로치가 있다고 말씀을 드렸는데 웨이브 투백 2.0 같은 어프로치도 있고 그거랑 유사한 휴버트의 약자가 히든 유닉 벌트에서 나온 겁니다. 그래서 그런 걸로 스피치 토큰을 정의를 할 수가 있습니다. 그래서 라지 랭귀지 모델에 대해 가지고서 스피치 토큰을 가지고서 스피치 데이터도 추가 파인 튜닝을 시킵니다. 그래서 좀 영어로도 조금만 설명을 드리면 we first start with a large language model and we can define speech tokens using some encoder based approaches like Hubert. Then we can do fine tuning using speech data. So originally it was a text-based large language model. Then we are adding some new tokens. Then the large language model is fine-tuned to those speech tasks. Then we can have a pre-trained speech language model. But if we only do those kind of simple fine-tuning, then the model performance will not be that good. So we add text-speech, speech-speech, text-text, speech-text, those kind of multimodal instruction following data sets. So we artificially generate those kind of data and we apply fine-tuning. 그래서 라지 랭귀지 모델이 처음에 프리트레이닝 넥스트 토큰 프리딕션을 하도록 처음에 프리트레이닝 된 다음에 사용자의 인스트럭션에 대해 가지고서 그런 기대되는 아웃풋을 시퀀스로 만들고 그런 인스트럭션 팔로잉이 잘 되도록 파인 튜닝을 시키죠. 그 단계를 거치는데 스피치 GPT도 LLM에다가 스피치 토큰을 추가를 시켜가지고서 파인 튜닝을 시키는데 파인 튜닝 자체가 프리트레이닝입니다. 그래서 스피치의 다음 토큰을 프리딕션을 하도록 프리트레이닝을 시키는데 그런 경우는 텍스트랑 텍스트 그 다음에 스피치랑 스피치에 대해서만 프리트레이닝이 된 거지 모델러티가 바뀌는 거에 대해서는 프리트레이닝이 된 게 아니니까는 인스트럭션 팔로잉 단계에서는 크로스 모델 인스트럭션 팔로잉 셋을 만들어 가지고서 파인 튜닝을 시킵니다. 그래서 이거는 아까 말씀을 드렸는데 처음에 랭귀지 토큰이 있고 거기에 스피치 토큰을 추가를 시켜가지고서 더합니다. So originally we have the vocabulary of the language token and we define the speech token, and I mentioned that speech tokens can be defined using some speech-based encoder only structure like Hubert. Then the final vocabulary will consist of both the language token and the speech token. So the entire token is defined as the union of the text vocabulary and the speech vocabulary. 그다음에 이거는 아까 지금 말씀을 구두로 지금 드린 거여가지고 스킵을 시키겠습니다. 그래서 스피치를 큐버트 같은 알고리즘을 이용을 해가지고서, 그러니까 스피치라는 것은 컨티뉴어스한 데이터고 그다음에 토커니제이션이 되지가 않는데 스피치 토큰을 디파인을 해줘가지고서 모델러티가 스피치로 바뀐 것을 프리트레이닝 시키는 것이 가능합니다. 그다음에 아까 크로스 모델 파인 튜닝에 대해서 말씀을 드렸죠. 그래서 스피치나 아니면 텍스트에 대해서만 프리트레이닝을 시키면은 모델러티가 바뀌는 텍스트 비그젠플은 나중에 나올 텐데 그쪽에 대해서 퍼포먼스가 좋지가 않습니다. 그래서 크로스 모델 팔로잉의 기그젠플을 지금 말씀을 드리면 인스트럭션은 listen to the speech and write down its content. 이렇게 요게 이렇게 인스트럭션을 해주고서 그다음에 스피치 클립이 그러니까 입력은 스피치로 들어가고 그다음에 아웃풋은 좀 텍스트로 나온 거죠. 그러니까 지금 게레렘인데 게레렘이 지금 원래는 텍스트 입력 항상 그다음에 텍스트 아웃풋만 됐고 그다음에 스피치에 대해서 프리트레이닝 지금 요 경우는 인풋은 스피치인데 아웃풋은 텍스트고 좀 이런 데이터에 대해서 지금 아직까지 전혀 학습이 안 됐기 때문에 이런 입력이 스피치고 아웃풋은 텍스트인 이런 데이터들을 저희가 생성을 해가지고서 파인 튜닝을 시켜야 되고 그 절차를 크로스 모드 인스트럭션 팔로잉이라고 부릅니다. 그래서 이런 것들도 이그샘플인데 입력하고 아웃풋이 전부 다 스피치일 경우도 있고 아까 말씀드린 대로 입력은 스피치고 아웃풋은 텍스트 이런 식으로 한 모델이 자유자재로 그런 스피치랑 그 다음에 텍스트를 다 입력으로 받아들일 수가 있고 아웃풋도 이런 식으로 할 수가 있고요. 그래서 이런 것을 꼭 스피치나 텍스트뿐만 아니라 위에서 나오는 EUG 시그널이나 그런 데도 비슷한 아이디어를 적용을 할 수가 있을 것으로 생각이 돼가지고서 저희 연구실에서도 그쪽 방향으로 연구가 진행 중입니다. 그 다음에 스피치랑 텍스트랑 그 다음에 EUG 데이터 같은 것들이 비슷한 정보를 가지고 있는데 아까 텍스트랑 스피치랑은 얼라이먼트가 안 맞다고 말씀을 드렸죠. 그래서 얼라이먼트를 어떻게 파는지가 그게 로스를 캘큘레이션 하는데 그런 중요한 이슈고 그다음에 파인 튜닝을 시킬 때도 데이터끼리 얼라이먼트가 잘 맞아야 됩니다. 그래서 그런 효과적인 멀티모달 모델을 만들 때 얼라이먼트를 어떻게 시키는지가 얼마나 모델 성능이 좋은지 그다음에 상대적으로 적은 데이터만 가지고서 파인 튜닝을 해도 그런 제너레이티브 모델이 성능이 좋게 나오는지 영향을 줄 것 같아가지고서 지금 저희 연구실에서도 연구 방향이 그쪽 방향의 연구를 하는 중입니다. So alignment has been an important issue in speech recognition because there is no clear alignment information between the speech waveform and text, And when we are doing a fine-tuning of the large language model to speech data, the same kind of problem will still happen. So the real question might be the efficient alignment algorithm. So in speech GPT, actually they didn't apply any kinds of explicit alignments, but in our we are trying to develop kind of more novel alignment algorithms to improve the model performance. And the multimodal generative resource is not limited to speech and text, but we can also extend it to brain decoding by incorporating some kinds of multi-channel EEG data from our brain signal. So now let's go to the model compression. So knowledge distillation, quantization, and low-rank approximation and pruning are well-known model compression techniques. So one of the most widely used model compression technique might be the quantization. So AP quantization is really easy, and this is probably everybody is using AP quantization because TensorFlow Lite supports AP quantization very well. So when we commercialized our speech recognition engine for Android phones, we of course use the AP quantization. But these days, for large language models, AP quantization might not be enough. So we are using a 4B quantization. So if you read the GPTQ paper, then they successfully used the 4-bit or 3-bit quantization to large language models like Bloom or OPT. And these days, 1 or 2-bit quantization is also possible. But if we do 1 or 2-bit quantization, then usually there will be some performance degradation. And when you apply 1.58-bit quantization to large language model, we usually apply the quantization only to the projection matrix and the dense layers. So for other parts, if we apply low-bit quantization, then the performance degradation will be large. So we apply 1-bit or 2-bit quantization to linear layers. And when we first commercialized our speech recognizer, we used the low-rank approximation. So at that time, as Samsung research, there was a leader named Dong-Suri, and he moved to Naver. So this is a case seems like he's reading some efforts at Naver to reduce the model size. And so he also did some work related to low-rank approximation and quantization when he worked for Samsung research. So in our team at Samsung Research, to commercialize on-device speech recognition, we did knowledge distillation, quantization, and low-rank approximation. And pruning is also well-known approach. But at Samsung, actually, we didn't actively use the pruning approach. So to use pruning, there are 2 different types of pruning. The first one is unstructured pruning, and in unstructured pruning, each individual weight will be pruned, and in that case, the matrix will be changed into a sparse matrix. So if we don't have a hardware which can do sparse matrix multiplication efficiently, then unstructured pruning is not that efficient. And structural pruning is removing a certain kind of block, like the entire layer or entire head. And these days, in case of large language model, it turns out that structural pruning works a little bit. So these days, structural pruning is gaining some popularity, but still quantization might be the most widely used approach. Yeah. So when we first commercialized our on-device speech recognition in 2019, we used the LRA, low-rank approximation, so we can do singular value decomposition, and we only select the low-rank portion that we can reduce the matrix size, and we applied AP quantization. But later on, to reduce model size, we applied large distillation for the second pass attention part. And these days for large range model, we tried quantization and pruning. But if we use pruning, then performance degradation is usually larger than quantization case. So still, I think that quantization might be the most popular approach. So this is the experimental results when we first commercialized our VOCA-based on-device speech recognition engine. And at that time, we used the LRA, low-rank approximation approach. So as you can see, we significantly reduced the model size. And when we apply quantization, then in some cases we apply quantization only to the weight, and in some other cases we can apply quantization not only to weight but also to the activation output. So if we apply the quantization to the activation output as well, then we can significantly reduce the computational cost. So if we apply quantization only to the weight, then we can reduce the model size, but still multiplication should be done using floating point numbers. But if we apply quantization both to weight and activation output, then we can replace those kind of floating point operations with integer operations. So as you can see, after we reduce the number of bits from 32 down to 8, we could reduce the XRT. So XRT means that how much time will be required to process a certain input. So RT means real time. So if XRT value is 5, it means that 5 times more than the real time will be required to process the actual input. And word error rate became worse a little bit, but not by a large margin. So I think that you're probably familiar with quantization. Quantization is also called Yangjawa in Korean word. So there are some equations about quantization, but this one is quite obvious. So I'll schema because lack of time. So there are two different approaches in applying quantization. The first one is a post-training quantization, which is the easiest way. So in post-training quantization, the model is first obtained, and after training is done, then we define the calibration set, and from the calibration set, we define the quantization step size or the data limit. So we are not performing any additional training, but in quantization aware training, we define some kind of fine-tuning data set, and after performing quantization, some kinds of training still goes on, and quantized coefficient will be used only for forward and backward propagation, and it will not be used in the weight update. So in model update, there will be 3 steps: forward propagation, backward propagation, and the weight update. But if we use the quantized value in the weight update, then usually the performance will be too poor. So we apply the quantized value only for forward propagation and backward propagation, and when weights are updated, then still floating point values will be used. So usually QAT shows better performance than PTQ. But if we use the AP quantization, usually PTQ will be enough. But if we want to do quantization using 4-bit or 2-bit, then without QAT, the performance will be too poor. So I will skip this part. So quantization criterion is that when you have the weight matrix, we introduce a scalar coefficient, and B is the binary matrix. So this one is an example of a binary punctuation, and we want to minimize this L2 norm. Then if we just solve the equation, then we can come up with this alpha value. So the optimal alpha value is actually the error norm, the average of the error norm of the weight matrix. And so the B value, the optimal B value is the sign of the weight matrix. So just solving the equation, we can come up with the optimal binary matrix and the weighting coefficient. And during the training, as I mentioned before, there were 3 training steps, like forward pass, backward pass, and parameter update. And the binarization is done only for the forward pass and backward pass, and for parameter update, still floating point values will be used. And I mentioned that if we solve the optimization equation, then for binary matrix, then it will be represented as the sine function, and sine function is not differentiable. So in the actual implementation, instead of using the sine function, we are using like a hard hyperbolic tangent function to represent the sine function. So if we differentiate sine function, then it will be the delta function. But if we define the sine function like in this way, then it's still differentiable. So in the actual case, we are using this kind of approximation, and I mentioned that this says punctuation can be done using only -1, 0, and 1. Then in that case, there are 3 bits. So if we do log base 2, 3, then the value is 1.58. So that's the reason why it's called 1.58 bit punctuation. So of course, binary punctuation might be the more optimal case, but if we use only 2 bits, then performance will be generally too poor. So we are using ternary punctuation. So this is the summary of today's talk. So in today's talk, I talked about some sequence-to-sequence modeling, like encoder-decoder approach, CTC-based approach, and transducer-based approach, and some NLP model as well. And I talked about speech GPT and discussed how the large language model can be extended to cover speech talk as well. So we discussed multimodal speech model, and also discussed model compression a little bit. Thank you very much for your attention.
So any questions? That's a lot of material. I have some questions. So I looked at the figure, and it seems like going from 32 to 8, you had a sort of question of maybe 4.
Yeah.
Is it 4?
Yeah.
So to be on device, I heard that you have to be, the size has to be less than 1 gig, or
Yeah.
1 gig. So the large language models are much bigger than that, right?
Right. Yeah.
So how can this be how can you have on device?
Yeah. So that's a very good question.
So in the previous slide, so the BAP computation is the case for speech recognition, and for speech recognition model, the model size is usually less than 200 megabytes. So the model size itself was not a big issue, but for large language models, actually the last year we tried 2 billion model to billion model, and to run the 2 billion model on our phones, then we needed to apply 4-bit quantization. So our objective is making the model size less than 1 gigabyte. And for speech recognition, actually, because the model itself is much smaller than large language model, still AP quantization is more effective because we are usually running the model on ARM CPU, and in CPUs we don't have any dedicated 4-bit arithmetic unit, but for large language model, our target is using NPU, and in NPU or GPU they can handle 4-bit arithmetic. So when we commercialized our large language model, at that time our objective was compressing 2 billion model and applying 4-bit quantization. But in our commercialized model, actually that approach was not successful. So in the newspaper, you probably read some articles saying that Samsung commercialized some large language model. Actually, that model size is actually less than 1 billion, and we still applied AP quantization. So that's the case for our commercialized model. But eventually, I think that on-device LLM, Samsung on-device LLM will be based on the 4-bit quantization, and in the future, I think that probably we will try to use 1.5 AP quantity. Yeah.
And another thing, I didn't quite, so sorry about this, I have one more question. So, you said forward and backward is quantization, and then you do parameter update,
Yeah.
floating point.
Yeah.
I didn't understand, so the parameter has to be in integer, right?
Yeah. So
I didn't quite understand. Yeah.
So that's actually a very good question. So if we apply quantization, then of course all parameters values will be stored in integer. But in Q80 stands for quantization aware training. Then during the training phase, we have both the original floating point values and the quantized values. And in the for propagation, we apply quantization of the floating point value, and we are using the quantized value for the forward propagation and backward propagation. So those calculation is the
two values.
Yeah. But after we obtain the gradient, we don't add gradient to the quantized value, but we are adding so in gradient update, usually the equation is like theta prime will be theta minus loading rate times gradient. So that value will be added to the original floating point value. Then after the floating value, floating point value will be updated, quantization is done once again before the forward propagation stage. So if we use only the quantized value for everything, then usually the performance will be
very bad.
too poor. Yeah.
Okay. Any more questions? 여기 질문 있어요.
Thank you for your speech. I just wonder, in speech recognition's part, the choice of CTC or transducer depends on the specific task, or something is just more used these days.
So President, that's a good question. So this is actually you are using the transducer-based structure because the usual transducer is showing a little better performance than CTC. So in CTC, it's not an auto-regressive structure, so usually performance is a little bit poorer than transducer-based structure. So for our commercialized engine, we are using the transducer-based structure, but CTC still has advantages. So in transducer structures, we have the feedback path, and then feedback path actually makes some parallelization very difficult to generate the next output, and previous data should be processed first in case of transducer structure. But in CTC, as long as we have the enough input parallel computation is possible. So CTC is much more efficient. So if we want to implement certain kinds of lightweight streaming speech recognizer, then CTC is more useful. So for our commercialized engine, we are the transducer, but for ultra light or on-device speech recognition engine, CTC might be more useful. And I think you probably heard about OpenAI Whisper, and in case of Whisper, the structure is the encoder-decoder structure, so the structure is still different. So for commercialized speech recognizers, some structures are based on CTC, and some algorithms are based on transducer, and some edges might be based on encoder-decoder structure, and those structures has its own advantages and disadvantages.
Okay, so let's. Oh, you want to ask? Okay.
Yeah, I have a question. Thank you for your wonderful speech. And in your presentation, you mentioned about the hallucination in your speech model. So could you share us some like how severity the hallucination in speech model, and how can you mitigate that?
Yeah. So hallucination is like kind of a very serious problem in large language model. So in generative speech model, actually for speech recognition itself, actually we don't suffer from hallucination that much. But in generative speech language model, actually the backbone is still language model. So when we are doing speech recognition or speech synthesis, then if some hallucination happens in large language model, then speech recognition result will be affected by that hallucination as well. So as an example, in speech translation task in machine translation, if we use the encoder-decoder structure, then usually we don't have a serious hallucination problem. But if we use the large language models, then in some translating text, actually large language model understands the concepts of the input, but based on some different way how encoder-decoder structure processes this. So some certain words will be removed, so some certain portion will be removed, and if we extend it to a speech model, then the same problem still happens. So in speech recognition task, some certain words will disappear, and some words which the speaker didn't say will be added. So even in the generative speech model, the hallucination problem will still happen. So if we use the CTC-based encoder only structure, then this problem usually will not happen, but in generative speech model, it will happen.
Okay. I think we're running out of time. So let's give our wonderful speaker a big hand of applause for a wonderful talk. And I think there's lots and lots of material that we can need to grasp. Thank you very much.